watch it again just for fun. But all right, so the quiz will be over sections 1, 2, and 3. Let's take just a little bit of time since we're coming back from 5 days off to just remember where we came from, where we're at this point. Okay, we've done sections 1 and 2. We're now going to do section 3. That'll be actually a big part of the quiz. Will be section 3. There'll be a calculator part and a no calculator part. Okay, so where did we start? When we started here in chapter 1, we were chapter 2, section 1. We were essentially, what you see on the board up here is we were saying, okay, we've done this stuff with the chart and this thing called the derivative and slope at one point, which means we have 2 points get really close together and all that good stuff that we did in chapter 1 with the connections between f and f prime and the chart and all that stuff. We still got to know all that, local max, min, whatever, okay? But that's kind of on the back burner right now, okay? Those connections and those kind of things. Right now our focus is let's investigate this idea of the derivative a little closer. Let's investigate this idea of 2 points getting really close together. So we said, okay, let's draw a picture of this. And we'll call point A where we want to do the slope. And matter of fact, we can graph that tangent line right there and right there. There it is. And that we want the slope of that black line, but we need 2 points. So we pick the second point, A plus H, and we make the green line. And then we say do the limit as H approaches 0. So that was the first thing we did. And then we did a bunch of problems where, and you'll have to be able to do these, we did a bunch of problems where we said, okay, here's a function, and we want to do the derivative at 2. And so we said, okay, let's use that formula, the definition of the derivative, f of a plus h minus f of a all over h, limit as h approaches 0, and let's do it. And there's a bunch of algebra involved, and we called this the long way, we came up with 70. Now 70 then is the derivative of that function at 2. Okay? And then we did, and so you got to be able to do that. We had some FOIL in there, some factoring, stuff like that. We said, okay, here's another example. Function is this. We want to do the derivative at 3, so we put a 3 in there. We do the limit as h approaches 0. We work it all out, and we get this. Okay? Then we said, well, wouldn't it be nice if instead of just having to go through there and do the slope at 3, what if we want to do the slope at 2? Got to do it all over again? Slope at 1, do it all over again? You know, how about if we found the slope for all points x? So that was easy enough. Then we said, well, let's just take that same picture, and instead of call that point A, let's call that point x. And have that same formula. And then let's go through what that would look like. And so we took an example. We said, well, let's take, we had done this example. We said, let's take x cubed, do the derivative at 4. So we went through there and we found it was 48. But then later, that next day, we said, well, what if we did this? What if we said, here's f of x is x cubed. What if we just found, instead of f prime of 4, what if we found f prime of x? So we just left an x in there. And we FOILed it all out. We got 3x squared, right? And we said, aha, I see a pattern, right? And we realized that, where did that 3x squared come from? Just bring the 3 down in front, drop the power by 1, right? And there was our shortcut. And so we had these shortcuts for finding the derivative. And what's really going to be important here for you is in the next several days is to not only get the big picture of what we're talking about, but be able to do the nuts and bolts algebra. And it's really easy to get so lost in the specifics of the algebra and stuff that you forget the big picture of what's going on. And this will just be a bunch of memorized, do this or do this or do this or do this, without any connections. And if that's the case, then you're going to be in trouble, okay? Because there's going to be so many of those little things. You've got to understand what it is you're doing at various times along the way as we go through this. Okay, so this is kind of tricky from that standpoint. So really focus on the big picture, even while you have to get all these details down. And of course, this is where, if you're good at algebra, it's a lot easier to focus on the big picture because you don't have to worry about foiling right and distributing a negative. If you keep screwing that stuff up, it gets frustrating, and then you lose sight of the big picture because you get focused on doing all the little algebra things right. So, Now that we've learned the shortcut, and again, this is kind of big picture stuff now. We just went through this whole long thing, we found 70. What did the 70 mean again? What did the 70 mean? The derivative of this, the slope of this at 2. But now that we know the shortcut, don't I know what d prime of t would be? What would d prime of t be if this is d of t? No, yes, okay, you're doing that one first. 30t, wouldn't it? I'm doing the shortcut now, right? So wouldn't this be 30t to the first plus 10? Right? The derivative of 10t to the first, bring a 1 down in front, right? Well, 10t is a line and the slope is 10, yeah. Wouldn't that be the d prime of t? So then what's d prime of 2? Put a 2 in for t. D prime of 2. If you know d prime of t, then d prime of 2 would be put a 2 in for t. And what do you get? Ah, awesome. 30 times 2 is 60. So that would clearly be our favorite way to do it, right? Rather than have to go through all this. The only time you have to go through this is, and maybe once or twice in the quiz, where it'll say use the definition of the derivative. Use the limit definition of the derivative. One of those variations. Somehow, if you talk about the definition of the derivative, we want you to go through the whole long process. Okay? But otherwise, if it just says find d prime of 2 for a function, do the shortcut and then plug the 2 in. Right? So there'll probably be some of that too. All right? So again, understand the big picture so you know what are the directions telling me and what do I need to do. Okay? Same thing on this one. What's f prime of x here? 2x minus 1, right? That'd be the derivative of this using our shortcut. And then we want f prime of 3. 2 times 3 is 6, minus 1 is 5, right? Okay, so by the definition, the long way, and then the way that from here on out, 90% of the time we'll do is this. We'll do our shortcut, and if we want f prime of 3, we do that. If I want f prime of 2, then we put a 2 in. F prime of 2, 7, put a 7. Okay, so that's what section 1 was about, was the point, you know, this stuff right here. Then section 2 was about learning these shortcuts. Okay, and now we're going to get into section 3. Okay, so one last thing I would like to review with you before we move on is a couple of these shortcuts. Whoops, right there. So here I've got 3 different ways I'm asking the same thing. This is saying do the derivative of this. This is saying find f prime of x if f of x equals this. Okay, same thing, do the derivative. Y equals this, so y prime equals what? Okay, those are 3 ways of saying the same thing. So you guys do it. Using our shortcuts and our little formulas that we already have talked about. Now, some of them may trip you up here yet, okay? Remember I showed you that website where you had levels 1, 2, 3, 4, and quite nasty? Yeah. Remember that, right? Okay, this would be this kind of thing. So there'll be a little bit of this on the next quiz. Not a huge amount because, trust me, Chapter 3 is full of rules, derivative rules that we'll have to learn. And we'll have a big test over just doing those shortcut rules, okay, of derivatives. But try these real quick. Just put them in your notes or something. Give you about 5 minutes. All right. Now you may not quite be done, but let's talk about these. Okay, somebody want to tell me number 1? 10. To the perfect. Power rule, the +3 doesn't really matter other than it's just a shift to the left, which means the derivatives will all be shifted to the left, or the slopes will all be shifted to the left. So you'll hear me a lot this year say, leave the inside alone. Now, it's very important that you understand what's the inside of a function versus the outside of a function. If I have e to the 2x, the 2's on the inside. If I have 2e to the x, then the 2's on the outside. If I have 2x to the 4th, is that 2 on the outside or the inside? It's on the outside. If it was on the inside, the function that we're talking about here is the 4th power function. If the 2 is on the inside, it would look like that. Okay? So it's important that we understand when it's on what's on the inside versus what's on the outside of a function. Okay? All right, so that's correct. Good. What about this one? -3 cosine 2x. Why is there a times 2 there? Kick out a 2 because the 2 on the inside compresses the graph. And since it compresses the graph, and to be honest, you don't have to memorize about the compressing. You should know that, but 2 on the inside compresses the graph horizontally. It's going to make all the slopes steeper by a factor of 2. So therefore, we have to get outputs from f prime that are twice as big, so we need a 2 kicked out to the outside. The 2 stays on the inside also because we always leave the inside alone, okay, like there, okay? So the 2, okay, so when I was talking about outer and inner of the function, whenever we do derivatives, you will hear me say this all the time this year, leave the inside alone. So whatever's on the inside, when you do the derivative, it'll still be on the inside, okay? Now we shouldn't leave it like that. We should write -6 cosine 2x. Now somebody in the other class said, I still don't get why that compresses whatever, and I said at some point you just don't worry about it, and you just memorize. If I'm multiplying a number times x on the inside, I've got to kick it out. Okay, now that'll become a little clearer when we get into chapter 3 and learn some things. But okay, now what about this one? Now you don't have to raise your hand, but my guess is there were some of you when you saw e to the x minus 3 that brought the x minus 3 down in front like this. You don't have to admit it if you did, but don't do that. What's the derivative of e to the x? E to the x, right? It's its own derivative. There's the power rule, where you bring a power down in front, only applies when you have x's raised to a numeric power. When you have x's raised to a numeric power, not when you have a number raised to an x power. That's an exponential function, and that's totally different. So the derivative of e to the x is e to the x. Well, what does this do? The -3. Shifts it right 3. Well, what have we been saying about the inside? You just leave it. So the derivative of e to the x minus 3 is just that. That's all it is. Now, if there would have been a 2 on the inside of that times that x, we'd have had to kick out a 2. And there'd have been a 2 sitting out there then. If there'd have been a 2 on the inside with that x, then any number that's multiplied on the inside times the x is going to get kicked out at the end after you do the derivative. So we'd have had to kick out a 2 then. All right. Plus. How do we have to write this first? That's x to the 1/3 power. Now we can bring the 1/3 down in front, which gives us 2/3. X to the -2/3, because you'd have 1/3 take away 1, 1/3 take away 3/3, which is -2/3. All right, and here we have minus, and then how do you write this? To the negative second power. X minus 3 squared on the bottom is the same as x minus 3 to the -2. You have to do that before you can do the power rule. You can't just try to bring that 2 down in front down there. That doesn't work. Okay, the rule doesn't say you can do that within a fraction. The rule says if you have x's raised to a power, now you can do it. So now we do. So we bring the -2 down in front, which will make that a +2. The inside doesn't change, and then to what power? -3. -2 subtract 1 is -3. There would be the derivative. Now, it's perfectly fine to leave it like that. You don't need to flip this down and get a positive power. You don't need to put that back into radical form. I don't care about that stuff right now. Okay? So you can just leave it just like that. All right. So for some practice on those, you want to go to that derivative back on the website, back on our School Fusion website. I've got this derivative practice number 1, and that's where you could go in and look at some of those. Okay, that won't be a huge part of the quiz, but there will be some with the power rule and be able to deal with those things. Okay, so with that said, let's move to let me see here. All right, so when we did the definition of derivative, we found out about this new thing here called the limit. This limit as h approaches 0. It is absolutely the most important thing in calculus. Without limits, none of calculus works because the whole thing is that this part is just the difference quotient, the slope between 2 points. Well, that's algebra 1. But when you let the 2 points become 1, which is what the limit does, that's when it becomes calculus. Okay? The 2 points get infinitely close together, and that's what limit does. And so we're asking, what is the value of this slope as h goes to 0, as the 2 points become 1? So without limits, we have nothing. We can't do derivatives. We can't do calculus. So it might make sense that we stop and learn a little more about limits. And that's what we're going to do today. So if you look at, and that's what section 2.3 is all about. So if you look up here on the board, I've got something here about limits. Now, all squares are rectangles, but not all rectangles are squares, right? All squares are rectangles, not all rectangles are squares. All derivative problems, by definition, are limits. Okay? They're this right here, by definition. Now, that doesn't mean that every time we do a derivative problem, we're thinking of a limit. You know, like we were just talking about. If I give you 4x to the 5th and ask you for its derivative, what are you going to tell me? 20x to the 4th, right? And you didn't do a limit there. You didn't have anything to do with a limit, right? But behind the scenes, what was happening was it was this. 4 minus 4x to the 5th all over h, limit as h approaches, right? I mean, that's a way we could have done it. If I just said use the definition and do it the long way, then we could have had to do this. And FOIL that out, that'd be a big mess with 5th power or whatever. A bunch of things would cancel. X to the 5th would cancel. H's would cancel. Then we'd plug a 0 in for h, right? And lo and behold, we'd come out at the end 20x to the 4th, right? Okay? So when I say that all derivatives are limits, I mean, I feel like it, but because the definition of a derivative involves a limit, technically, all derivatives have something to do with limits. But not all limits have anything to do with derivatives. Some limit problems are just limit problems. Okay? What is the output of this thing getting close to as the input is getting close to this other thing? Okay? So what we're going to do today is kind of a little bit of a side trip. The next couple days, we're going to focus on just this idea of limits. Okay? So the stuff with the chart and F prime kind of is on the side a little bit. It'll peek into some of the problems every so often, right? So we still need to know that stuff. And every once in a while, we'll pull out a special limit problem that also happens to be a derivative. Okay? But for the most part, for the next couple days, we're just going to focus on this idea of a limit. All right? Because it is so crucial to the definition of the derivative, it might warrant some extra study. Okay? So, we're going to watch a couple of little videos here that I've put a link right here that says videos about limits and continuity. They're really pretty good. The guy is somewhat interesting to listen to. And now, there's one here that says the difference quotient, which is just going through that whole f of a plus h and let the 2 points get close together and stuff. I don't think we need to listen to that one. But you certainly could. And then there's some others about power rule. You can look at that if you want to, whatever. But the ones I really like are the ones up here about limits. Because limits is, for some reason, limits is kind of a hard idea to totally grasp. And I think he does a really good job of putting this together. So we're going to watch the first three of these, and I'm going to kind of stop at various points along the way to talk about some other stuff. All right.
You may have heard a lot of talk about limits, but the plain fact remains, most people don't understand what a limit is. So for now, we're going to focus on what is a limit.
We're not talking about derivatives here in this section.
In basic terms, a limit is a height that a function intends to reach. That's pretty important, so let's say it one more time. A limit is the intended height of a function. Now this might give you pause. You might think, how am I supposed to know what height a function intends to reach? I don't even know what my intentions are most of the time. How am I supposed to discern the intentions of a function? That's a good question. And the fact that you don't understand exactly what I'm talking about is because all of the functions you've been dealing with, or at least most of them, have had their intentions completely clear. If a function intends to reach 3, it reaches 3. If a function intends to go 6 units high, it goes 6 units high. There hasn't been a lot of mystery so far. So I understand that you might be a little confused, but you've dealt with function heights a lot, so we might as well review function heights a little bit and then get into exactly what I mean by intending to go to a certain height.
Okay, this idea that he says about how the intended height of a function is really the critical key concept to a limit. It's not about what the height of the function is. It's not about what the y value of the function is, because many times it's undefined. Think about the limit examples we've done when we worked at the long way. At the end, when we get done, how do we find that final answer? We put a 0 in for h. Well, why didn't we just put a 0 in for h at the beginning? Because you can't divide by 0. See what I'm saying? So what happens is the limit we're trying to find is undefined initially. Until we do some algebra, or look at a table, or a variety of other techniques that we're going to talk about, we can't tell what the intended height is, or what the function values are getting close to. Okay.
Let's start by looking at a very simple function graph. What I have here is the function f of x equals x squared, basic parabola. You'll notice that the function changes heights all throughout its domain. That's a very fancy way of saying that the function reaches many different heights based on whatever the x value you're looking at happens to be. For example, what if I look at the function height that corresponds to x equals 2? Well, it's not very difficult to figure out exactly how high that function is going to be when x equals 2, because all I have to do is plug in that x value into the function to figure out what that height will be. So, if I plug 2 into x squared, I get 2 squared, or 4. This means that the function reaches a height of 4 whenever x equals 2. Pretty simple. But now I can create my first very basic limit statement, and that is the limit as x approaches 2 of f of x equals 4. This just means that whenever I'm getting very close to the x value of 2, my function is getting very close to the height of 4.
Now, those arrows are really important that he drew there. Now, later on, he's going to do an example with cars, and we'll think about it that way, because I think it's a good visual. But as he says, when you plug a 2 in, you get out a 4, but that's beside the point. Because most of the time, like here, we can't just plug a 0 in for h at the beginning. On some very simple ones, we can do that. But now notice, see how this doesn't have anything to do with derivative? Because it doesn't look anything like this limit, right? They look different. This is a special limit that also is a derivative. We're just talking about other just ordinary run-of-the-mill limit problems, and this would be the simplest kind of all, where you just plug a 2 in, you get a 4, and that's it. That's the limit. Okay? Won't be very many like that on the quiz.
There's nothing really earth-shattering about what we just learned. But that changes when we examine functions that do not reach the heights they intend. Take, for example, this function. G of x equals the fraction x squared minus 6x plus 8 divided by the quantity x minus 2. Here's what the graph looks like. It looks like a plain old line. Or does it? If we zoom in, you'll see that it has a hole in it at the coordinates 2, negative 2. The hole exists because plugging x equals 2 into the function results in 0 divided by 0. And we know that dividing by 0 is a very bad idea. It breaks mathematical laws that we really can't even get into here. However, though this graph has a hole in it, it still possesses a limit when x equals 2. Clearly, the graph intends to reach a height of -2 when x equals 2. Even though that graph doesn't actually reach that height, it doesn't matter. The limit still exists, and we can say that the limit as x approaches 2 of g of x is equal to -2. This begs the question, when exactly does the limit exist? We examine that in the next module.
Okay, so now, that's what's been happening in these problems, right? When we got 70 and we got 48 and some of these other things we were getting over here, there was a hole. If we were going to graph those, there's a hole in the graph. On those worksheets that we did last Tuesday, it was always undefined on that table. There's a hole there. So whenever you get, one of the things that you might make note of here is that any time you get 0 over 0, that usually means a hole in the graph. I mean, for our purposes, really every time. We can almost think of it every time. It's not necessarily always, but basically what this is going to mean, when we see 0 over 0, another word for this is indeterminate. It means you can't determine. Indeterminate means you can't determine what's going on just from that information. You need to do more. So keep going. And now for us that might mean boil it, factor, cancel, conjugate method, get a common denominator, all those algebra things we did. It might mean go to a table on your calculator. All those things we're going to be talking about here today on those things. All right. But did that make sense? There's a hole in the graph. You can tell that the y values are getting closer and closer to -2 there. Okay, as x was getting close to 2, there just wasn't a value at 2. But we don't care about that. We don't care that there's not a value at 2. It's the intended y value. It's where the function is heading towards that we're interested in. Okay. Go on to the second one.
Now you have some idea of what a limit is, and we need to talk about when does a limit exist. To illustrate my point before we get started, let's set up an example. Let's say you and a friend are going to meet for dinner, and you're meeting at a diner that's centrally located between the two of you. If you live east of the diner, and your friend lives west of the diner, and you both want to drive to meet there, ideally, the roads which lead to the diner will lead you to the same place. If you travel towards the diner from the right, or east, and they travel towards the diner from the left, you should meet up in the same place. Mathematically, this is basically what a limit is. A limit exists if you travel along a function from the left side and from the right side towards some specific value of x. As long as that function meets in the middle, as long as you arrive at the diner, as long as the heights from the right and the left are the same, then the limit exists.
Okay. Very important what he said there about from the right and the left. Whenever we do a limit problem, we're saying that when we say as h approaches 0, we mean as the inputs, h, get closer and closer to 0 from the left of 0 and from the right of 0. And that's why in the table we want to be able to see both sides of that. Okay? So let's keep going with this.
Now it's time to get down to the brass tacks and look at this mathematically. Take a look at the graph of this function f of x. Visually you can see that it's got a break in it at x equals 4. So, if we travel towards 4 from the right, we will arrive at a height of 2. However, if you travel towards 4 from the left, you will arrive at a height of 1. This means that no limit exists for f at x equals 4. Let's go back to our diner metaphor for just a second. Notice that as I'm traveling along the road from the right, I end up at a height of 2. But if you travel along the road from the left, you end up at a height of 1. These heights don't match. We won't both arrive at the diner, and no limit exists. We call the height at which we arrive from the right the right-hand limit of f of x. as x approaches 4 from the right. And we denote this with a little plus sign in our limit symbol. Our height that we arrive at from the left is called the left-hand limit of f of x as x approaches 4, and it is denoted with a little negative symbol. Mathematically, in order for a limit to exist, both the right and the left-hand limits must be equal.
Okay, so now let's investigate this a little bit. Oops.
Now let's change this function just a little bit. Now you have some idea of what a limit is, and we need to talk about when does a limit exist.
All right, I'll let that run for a second. All right, so let's examine a little bit of what they were just talking about. So, the file that I sent to you is called one-sided limits. Okay, and that's what he was talking about right there at the end, when he said the limit from the left had the little negative sign up there, and the limit from the right had the little plus sign up there. For the limit to exist, the two have to be the same. The car on the left has to meet up with the car on the right. Okay? And so when we do these limit problems, graphs are the easiest ones to do. Right? Graphs are the easiest ones because you can visually picture the cars coming in together. Right? You picture this car here and this car here, and they don't meet, so limit doesn't exist. Let me say a word about does not exist. That's different than undefined. Okay? A function is defined or undefined. If there's an output, it's defined. If there's no output there, it's undefined. Okay? That's different than limits. They exist or do not exist. If the limit exists, there's some number for your answer. If the limit does not exist, that's because they don't meet. Okay? At a point, at a place, at a number. And so there's no output, there's no number. So we say the limit does not exist. But that function we were just looking at there, I mean, isn't that going to be pretty obvious to see? I mean, let's go back. Let's see where he's at here. Okay. All right. So he was just, okay, I'll let that run. But if a graph's going to look like that one right there, what type of function's it got to be? It's going to have that big break in it. Doesn't it have to be a piecewise? I mean, it's going to be pretty, I mean, some problems, I'll just give you a graph. And to me, those are the easiest. Look on page 110 and 111 in your book. 110 and 111. Okay? And that's some of the homework problems. So look at the graphs around those pictures. You see? Look at those graphs. I mean, clearly those are piecewise functions, right? I mean, those aren't going to be like an x cubed or some simple kind of function. It's going to be a piecewise function, okay? But when you get one of those graph kind of problems, you're visualizing the cars, you know, and coming in. Okay, I think those are the easiest ones to do. But what if you just have a function? So what if I gave you this? What if I gave you f of x equaled, and then I gave you x cubed, and I gave you 2x, and this one is if x is greater than or equal to 2, and then this one is if x is less than 2. So what if I gave you that? Now, one thing you could do is graph it, right? You could draw a graph of that so you could picture the cars coming in. But I would say that you don't even really need a graph of that. Okay? Let's do the graph first, because maybe that's the easier one to see. So if you could draw the graph of this, you'd say, okay, 2x. Well, that's a line, goes through the origin, has a slope of 2, and that's till x is less than 2. So that's still right there. Wouldn't that have to have an open circle right there? Okay, and what would this y value be right here? Where that open circle is? What would that y value be? 4, right? Even though it doesn't hit that point, that would be 4. Okay, and then what about x cubed? X cubed is going to start at 2. So where's that going to start at? That's going to be up here at 8, right? And then it's going to, now what's x cubed? It's kind of that S-shaped curve, so it's just taking off and kind of going like that. It's curved, but it's, you know, you can exaggerate the curve, but it's, you know, it's whatever. And there'll be a closed circle there. Now there's clearly a gap there. Well, the two cars aren't going to meet, are they? So what would we say if I ask you, what's the limit as x approaches 2 of that function? We'd say does not exist, because the two cars don't meet. What if I said as x approaches 2 with a little negative? That means that as x approaches 2 from the left, what would you say? You'd say 4. Even though there's a hole there, we don't care. It's intending to reach 4. It never gets there, but that's okay. It's getting closer and closer to 4. And what if we said 2 from the right? The limit would be 8. but the limit at 2 means it has to come from both directions, we would say the limit does not exist. Okay? All right. Now I think it should be ready to go here. Yes?
So if you don't have the positive and negative sign in the limit, that means that it doesn't exist.
Okay, back up there. If you do not have the plus or the negative sign in your limit problem, it means the limit from both sides of 2. That's the one that may not exist. The limit from the left and the limit from the right are almost always going to exist. You get what I'm saying? Because from the left or from the right, the car is going to get somewhere. And from the left, the car is going to get somewhere. The question is, do they meet? That's when the limit exists. So if it just says as x approaches 2, what I call a normal limit, right? The others are on one-sided limits, from the left, from the right. But if I just have x approaches 2 with no little signs there, it means do the cars meet? From the left and from the right. Okay? Now, the only exception to the car is going to get somewhere would be a graph like 1 over x, if you had a vertical asymptote. If you had a vertical, and we won't get into infinity ones a whole lot right now, but if I had the graph of 1 over x, which goes like this, and goes like this, and I asked for the limit as x approaches 0, well, the car on the right's going to infinity. The car on the left's going to negative infinity. They're not going to meet, right? And so we would say the limit does not exist. Probably from the right, we would say, as our answer, we'd say positive infinity, because that's where it's going. And from the left, we'd say negative infinity. But the limit itself, as x approaches 0, we'd say does not exist because the car is going to meet. Okay? All right. Oh.
Does possess a limit. Can you see why that's the case? It's because the function no longer has a break at 4. Now, there's something to be said here. The previous function did not have a limit at 4. It did have a limit at many other points. For example, a limit existed at 1, at 2, at 5, at 0. All these x values showed locations where the graph did not break. In essence, a graph will not possess a limit if it breaks at the given x value. That's why our new function does possess a limit at x equals 4. Now, let's go back to our diner example one last time. Let's say we're traveling towards the diner. We both arrive at the same location, but the diner isn't there. Maybe it's caught fire or something. Does that mean the limit doesn't exist? The truth is, the limit will exist even if the diner's not there, because you still arrived at the same place. In other words, mathematically, a limit can still exist if your destination is a hole in the graph, because it doesn't matter whether or not the point is actually there. What matters is that you arrived at that point, coming from the right side and the left side. In conclusion, a limit exists on a graph if you arrive at the same height coming from both the right and the left side of the given x value.
All right. Now, so let's take this example that we were just working on here. So one of the things they said that's important. So if I take this example that's broke right here, if I change this and just ask for the limit as x approaches 1, what's the limit on this piecewise function as x approaches 1? It would be right there, which is 2. And the cars would meet right there. And, right? And the diner's even there, right? But it's not on fire and it's not burnt down or anything. Now, but let me back up a second. I meant to do this before we watch the rest of that other video. But what if this graph was not here? Okay, pretend the graph wasn't here. I go back to what I said earlier. I still think we should have been able to answer this question without the graph there. So let's go back to where I asked for as x approaches 2. And just look at this. Why didn't the limit exist? This one, because this car was coming down at 8, this car was coming at 4. Couldn't I got that from just this? By just plugging a 2 into here and a 2 into here. Now, another thing I might comment on is this is the part you really focus in on here, right? That's where the graph breaks. If it's going to break, that's where it breaks, is at 2. So when I ask for the limit as x approaches 2, I say, oh, okay, well, on the left side, when x is less than 2, I put in a 2 here, I get 4. On the right side, after 2, I put in 2, I get 8. Oh, yeah, they're not meeting because they're at different places. Now, what if I change this function? Well, and then let's put x approaches 1. and pretend you don't have the graph here, what would you be looking at as x approaches 1? You're looking at the bottom one, because that's when x is less than 2. So the bottom one, you'd say, oh, as x approaches 1, yeah, that's just this line. You plug in a 1, 2. It's easy. Okay? Now, let me change it. Let's change this from x cubed to x squared. Now let's do the limit as x approaches 2. What's happening? You get 4 both ways. So what's the limit? So the limit is 4. What you have there is you have a line until here, then you have a parabola, but it starts right from that same place. So you still have a piecewise function, but the two pieces, like they did in their picture, they brought them together. Now the limit does exist. So again, without a graph, I still could have done that. I could have looked at this and said, oh yeah, at 2, this one is 4, and this one is 4. So when one takes off, it takes off from the same place the other one is, so the cars will meet right there at that spot. Okay, now there's one of your homework problems that has, I think it's the very first one, that has something like this. It's got x squared when x does not equal 3, and it's like, I don't remember, 7 when x does equal 3. It's that piecewise function. Now, tell me what the graph of that would look like. It'd be a parabola, right? Except what? What would be happening at 3? There's a hole there. That's one way you can have a hole in the graph. Now they're going to show you another way, another type of function that has a hole in the graph. These ones we've been doing have had holes in it. If we were to graph them, they have holes in it. But this one's going to have a hole right there at 3. 3 what? 3, 9, right? At 3, 9. There's going to be a hole right there, because that's a parabola x squared. Okay, and then what's this mean? So right here, at 7, there's just a dot, right? This function, when x is 3, is 7. But everywhere else, it's x squared. So it's that picture. So what would that be like? That'd be like the diner burned down, and then they rebuild it somewhere else. Right? Where are the cars going to meet? So what would be the answer to this one? The limit as x approaches 3. The answer would be 9. What would f of 3 equal? If I ask you for f of 3. F of 3 would be 7, because that's asking for the output of the function at 3, which is 7. But the limit of this function as x approaches 3 is 9. That really shows the difference, why we don't really care what the output is, even though the output often is the limit. In just normal, random, everyday functions, whatever the output is a limit, because that's where the cars would meet. But here would be an example where the cars would meet at a different place than what the output is. But where the cars meet is what we care about. So they would meet at 9. There's no road to the new diner. I don't know how they're going to get anybody to go there. But anyway, right? I mean, the limit is 9. But it's going to be pretty obvious when you have one of those situations, because the only way you can have a graph that looks like this is to have some sort of piecewise definition, right? So, I mean, it's not like they're going to sneak up on you, or it's not like you're going to look at a graph of a cubic or something like that and think, is there a hole with a dot somewhere else? I mean, the only way you can have one of those is for it to look something like this. So it shouldn't be a surprise when you see one of those. Okay, so that's kind of that idea about limits. They're going to go on and talk about the holes in the graph here a little more. And again, it might, for some of you, as you go through this in the next couple of days, it might be worth going back and rewatching some of these, because I think he does a good job. We're going to watch one more. This gets more into the
Once you
algebra.
determine whether or not a limit exists,
Okay.
the next logical step is to try to figure out what the heck that limit is. So that's what we'll be focusing on in this section. How do you find a limit? The fancy word for finding the value of a limit is evaluate. So when you see the direction evaluate, basically you should be expecting to get the numerical
We
answer.
already talked about graphs.
There are 3 major ways to evaluate a limit. They are substitution, factoring, and the conjugate method.
We would add common denominator.
We're going to go ahead and start with the easiest one, which is direct substitution. It is just as easy as it sounds. We'll take an example. Here's one. The limit as x approaches 0 of the fraction x squared minus 1 divided by the quantity 2x plus 3. In order to evaluate this limit, all you've got to do is plug in 0 everywhere you see an x. So we'll put in 0 in the numerator and in the denominator, and we end up getting negative 1 divided by 3. So our limit is negative 1/3. It's as easy as that.
Okay? Now, notice we've been doing limits as x approaches 2. We've talked about x approaches 4. This one said x approaches 0. Back to our derivative just for a minute. Would we ever have anything other than h approaches 0 here in a derivative? You don't seem too convinced. Why do we have h approaches 0 here?
Got their cow on their point.
Yeah, because h is the distance between our 2 points. We have 2 points here, x and x plus h, and we want those 2 points to become 1, and so we want h to be 0. What I've seen people get confused when they do these derivative problems is that if I'm asking you to find f prime of 2, all of a sudden you think you're supposed to do h approaches 2. No. That 2 goes right there and right there, right? The h will always be approaching 0 in our special limit that is a derivative. But in ordinary run-of-the-mill limits, x could approach 0, it could approach 2, could approach 4, could approach whatever. Okay. All right, so here's just simple substitution. You plug a 0 in, it works out to negative 1/3. That means that in that graph, the point 0 and negative 1/3 is where the cars would be. Okay, you don't really have to worry. When you get an algebra one like this, you plug a 0, it comes out, that's what you go with. That would be your limit. Won't be very many of those on there, but that's always the first thing you try. Always the first thing you try is direct substitution. Here, if we put a 0 in right away, what do we get? Undefined, because we get 0 divided by 0. And like we said earlier, that means keep going. Try some algebra, try something, and that's what he's going to talk about now.
Unfortunately, not all limits are this easy. And you've already seen one for which that's the case. Remember that function that we were dealing with in the first section of this chapter? In case you don't, here it is again. A limit as x approaches 2 of the fraction x squared minus 6x plus 8, all divided by the quantity x minus 2. We looked at this before. It had a hole in it at the coordinate 2 comma negative 2. And we concluded from that that the intended height was negative 2, making it the limit. However, it would be nice to be able to figure out why this is true mathematically. And to do that, we'll have to use the factoring method.
What if you didn't have
As
that
you can
graph?
see, and as we saw before, direct substitution results in 0 divided by 0, which is not allowed. So we'll have to resort to this new method. We'll use the factoring method because the numerator of this fraction is factorable. If we factor it, we'll get x minus 4 times x minus 2. Can you see why that's a good idea? Well, the reason is because now the numerator and the denominator both contain the term x minus 2, which I'm going to cancel out. This leaves
In our
the
limit,
limit as x approaches 2 of x minus 4.
What happened at the end
This
was
is
good.
much simpler to solve because now you can
And
use
h is
substitution.
canceled, right?
And when I do, I get 2 minus 4, which is equal to negative 2. Remember, we knew the limit was going to be negative 2, and we're right. Feels good to be right.
Okay? See, that's where the h canceled out for us. We put a 0 in here, we get 0 divided by 0, because that h. Once the h canceled out, we were good. Same thing here. When you plug a 2 into here, then 2 minus 2 is a problem. That's 0. So what happened? You factored, you canceled, and there you go. See, when he told us earlier in the video, he just gave us the graph of this. It was a line with a hole in it. Well, that's easy. We see the 2 cars coming. Here's where they meet. There's our limit. But on our quiz, there's going to be a calculator part and a no calculator part. Okay, on the no calculator part, I'll probably do these 2 things. I might give you some graphs, kind of like the ones you were looking at in your book a minute ago. Give you some graphs, ask you some limit problems. On this, on the algebra ones, we'll look something like this. Okay? You got to find that limit. You don't know what the graph looks like. You don't have a calculator to graph. So you do the algebra, and you find it that way. Okay? Now, one of the algebra things is factoring. We've already done conjugate, and we've done common denominator. He's going to go through a conjugate example.
If the substitution method fails and the factoring method fails, you're not without hope. You can still try the conjugate method. Before we talk about the conjugate method, though, we might as well figure out what a conjugate is first. Take a look at this expression, the square root of x minus 4. Now, this is a plain old 2-term expression. However, it is easy to make the conjugate. All you do is change the negative sign in the middle to a positive sign. The conjugate of the square root of x minus 4 is the square root of x plus 4. That's all there is to it. Now, what if you see an expression like this in a limit problem? For example, this one is often. The limit as x approaches
Jot that
16
problem down
of the
on your paper
fraction,
somewhere.
the square root
We're
of x
gonna use it.
minus 4 divided by the quantity x minus 16. Well, what we'll do is multiply the top and the bottom of the fraction by the conjugate of the radical
You
expression,
don't have to write
which, as we said,
just do
was the square root of x plus 4. Now, the magic of this is that as you multiply out, the numerator will actually become x minus 16. You don't want to multiply the denominator out. Leave them as separate factors. Since I have x minus 16 in both the numerator and denominator, I can cancel them, just like I canceled like terms in the factoring method, and I'm left with a limit as x approaches 16 of 1 divided by the square root of x plus 4. Do you see why we didn't want to multiply out the bottom? It makes simplification much easier. Now I'm able to plug in 16. Substitution works. When I do so, I get 1 divided by 8. So the limit as x approaches 16 of my original function is 1/8. And that's the conjugate method.
Okay, so what we got there is just what we were doing earlier. When we did our f of x plus h stuff and we got 70 and we got 48, we did the same thing. We factored and we did a common denominator, we did a conjugate, and we worked it through and we got that limit, okay? But I want you to I want you to see the big picture of all this, all right? Understand that when we do a limit problem, there's a lot of ways to get that limit, a lot of ways to find what is the intended height of that function. If you have a graph, that's the easiest one. You just picture the two cars, and if they meet at a y value, that's the limit. If they don't meet, limit doesn't exist. We got the limit from the left is the car on the left. What's it doing? Car on the right. What's it doing? So we got graphs. That's pretty easy. If we don't have graphs and you're not allowed to use a calculator, it's going to be one of these algebra techniques we've been talking about. Okay, we'll practice more of the algebra tomorrow. All right. So last thing I want to talk about is what about when we do use our calculator, and that's where that worksheet we did last Tuesday with the tables and stuff is going to come in. All right. So I would like to, at this point, let's take. Get your calculators out and make sure you're logged in. Who wants to be presented? Let's see. Kingsley, you. All right. So, let's go ahead and go to your home screen. And go to your graph, go to the graph page on the scratch pad there. All right, and here is the thing we left off with when we were doing in class the other day. All right, so now what I want to do here is I want to do that same function that we just ended with on the video. That square root of x and all that. So let's go into your F1. And let's delete that. And let's put that function we just had. What was it? Square root of x on top. Minus 4, was it? Make sure you arrow, make sure you arrow outside of the square root. On the bottom was what? X minus 16. Okay, and go ahead and hit enter to graph that. Okay, now it's way, way down there. Let's adjust our window here. Let's, and we want to do this as x approaches what? We want to do the limit as x approaches 16. So why don't we make our x's, let's make our x's go from, say, -2 to 20. Because we want 16 to be in there. And our y's, we really don't need all that y space. I don't know, negative, I mean, it's way down there. I mean, let's go -5 to 5 maybe. The window doesn't matter so much for what we're going to do here in a minute. Now, if you still have your table up on your screen from before, hit Control-T just to get it off of there. If you still have the table, remember we had that split screen, you can hit Control-T, it'll go off there. Okay? Now, let's talk about this a second. So what we want to do is we want to see the limit of this function right here as x approaches 16. Again, big picture, what is that saying? It's wanting to know what heights does this intend to hit when x is getting close to 16. Now, the first thing he talked about is direct substitution. So on our calculator, what would be the equivalent right now of direct substitution? What would be the thing we would want to do? The limit as x approaches 16, that would be direct substitution. Trace to 16. We'd want to plug a 16 in for x. And the way we would do that is trace. So go to menu and trace. And what do you expect to have? It's going to be undefined, isn't it? Because we can already tell. So we type a 16, we hit enter, and sure enough, it's undefined. What's going on there? There's a hole in that graph, right? Now we can already tell that, are the two cars going to meet? Clearly, the car is coming this way and the car is coming this way, and they're going to meet. The question is, what's that y value there? Well, one thing we could do is just hit the left arrow real quick. Just hit the left arrow to go left of 16, 0.125. So now you might be getting different numbers. We came up with 15.7 in the other class. It depends on what your trace step and settings are or whatever. I don't care about that right now. We can go to the right, because we want to see the car on the left and the car on the right. And it's pretty clear that it's like 0.125. And is that, what was it supposed to be? Wasn't the answer supposed to be 1/8? Isn't that 0.125? I believe that is. 1/8, I think, is 1.125. So do you see how that comes together? So we have that algebra way of doing it. What I don't want to have is when you do the algebra and you get caught up on this algebra, you kind of forget what 1/8 means. What are you doing? And I want you to visually see it as well. Okay, so you see this. But on the quiz, on the calculator part of the quiz, if I give you this problem, what's the limit of this as x approaches 16? In the direction, you'll say use a table or a graph. I really mean use a table. And what I want to see is, so hit Control T, and that brings up a table. And now we got x's like 0, 1, 2, 3, and so forth, so on. What do I want to do at this point? I want my x to be at 16, right? So where do I need to go right now? Well, yeah, you could, but there's a better way than to start going up and down in your table right now. Remember what we did last Tuesday? Turkey makes you forgetful. While your table is boxed in, and if it's not, go ahead and click here. Go to Menu. Go to Table. Go to Table Settings. Number 5, edit. And start our table where? At 16, right? We're doing as x approaches 16. Now, on Tuesday, we were always putting the table start at what? At 0, right? Why? Because all of our limits were these derivative limits. They were all the limit as h approaches 0, right? And remember, we were pretending the h was x, right, when we did these problems? Because we had 4 plus h minus f of 4. So the h was an x, really, when we did it. But this is where, that's our table start. And then what do we do for our table step? 0.0, at least 3 zeros. So 0.0001. Okay? That's how I would do that. Okay, now on our worksheet it was nice because they were all at h equals 0, so our table was always right. So every time we put in a new function, our table was good. But now, when we change it as x approaches 16, now what I tell you to do next, once you have this table on your screen, arrow up 2. Why the arrow up 2? So you can see the car on both sides, right? You need to see before and after 16. So this would be the car on the left, 15.999. This would be the car on the right. And now you look at these numbers, and clearly, even though it's undefined right there, because there's a hole there, the diner has burned down, but the car on the left is coming in here at 0.125, the car on the right is coming in at 0.125. So on your paper, I would want you to copy down that table, and then that would show that your answer is 0.125. And you'd write that as your answer. Matter of fact, on the test, I might even give you the answer. You know, I might say the limit of this as x approaches 16 equals 0.125. Justify that using a table. Okay? And so I'd want to see that, right? Because it's no big deal if I don't tell you what the limit is supposed to be, because you can just go on the calculator side and just type limit, right? I showed you that the other day. There's a template there. You just type the limit, and it'll just come out. Okay, but I want to see that. I want to see a table. So I want you to understand, again, the big picture of how this works. Okay, so these are just limit problems. That's just an ordinary old limit problem. What is this function right here approaching? What are its outputs? What are its heights? What are its y values as the x's are getting close to 16? If we have a graph of it, we can see pretty easily. If we don't have a graph, maybe some algebra. In that case, it needed the conjugate method to work it out. Or we got this idea of table. Now, why would I make you do a table? Well, I want you to see all things, but sometimes these functions are too complicated to use algebra. Sometimes these algebra methods we've been talking about don't work. Okay? So then you don't really have a choice. You know? Or that it's beyond the algebra that we know how to do or really care about getting into right now. So we can go to a table, we can look at it, and we can see. All right. That's kind of it. I think what I want to focus on today then, in your homework, is this idea of graphs. And really the idea of graphs, a simpler one. Do the cars meet? Where are the cars at? So what we're going to do, and then tomorrow we'll focus on using our calculator for some tables. We'll focus on some algebra, that kind of stuff. So the homework, if you're really caught up and up to speed on everything, which might be iffy with Thanksgiving break and everything, it's going to be pretty short. But use this opportunity to go back and review some of that other stuff. So your only homework that I'm going to assign and then be checking tomorrow is where it says 2.3. Now it also says algebra worksheet, but we're going to save that and we're going to do that tomorrow. All right? So 2.3. Now, again, that itself, you might be done with before you leave the room. Okay? But use this time, because this quiz is not an easy one. Okay? I thought the last quiz was kind of an easy one. I don't think this quiz is probably as easy. So use this time before tomorrow to go back and practice some of those derivatives the long way. You know, the f of x plus h minus f of x, and look back over those. Practice common denominator. We're going to get some algebra practice tomorrow, but the practice how that works the long way. That was back in section 2.1. Section 2.2, practice some of those power rule problems, like we did earlier today. The shortcuts. Practice some of those shortcuts. Okay? Okay? Oh. Well, that would be surprising. I don't, I can't. Yeah, I can't imagine that. But I guess I could. I mean, he might know better than I. Well, yeah, I mean, he's not an idiot. You know what I mean? So,